Hi. Section 2.3, the precise definition of a limit. In the last section, we defined the limit intuitively. In this section, we'll define it more precisely, more mathematically. Okay, let's begin with this example. We choose the function fx equal 2x minus 1, and we'll try to see the behavior when x is around 4. So here, if x is close to 4, then now 2x will be close to 8, and this f of x will be close to 7, so that we defined intuitively here the limit of fx as x approaches 4 is 7. We did this definition in the last section. Now, we have a question here. How close to 4 does x have to be so that f of x differs from 7 by, for example, less than 1 unit? And here the question is, now, what values of x is satisfying this inequality, basically? So we'll try to solve this, we'll try to answer this question, and we'll try to see in some now another side of the limit, so that we'll try to define the limit more precisely. Okay, let's try to solve this question. F of x is 2x minus 1, so that the absolute value of fx minus 7 can be written in this way, and along with the algebraic simplification, we reach at that. Now this inequality can be written in this way. 2x minus 8 is now from minus 1 to 1. And by adding, we reach this inequality. And by dividing by 2, we can reach at this final inequality. So x is between 3.5 and 4.5. Then that inequality will be satisfied. Whenever you choose x inside this interval, always the difference between f of x and 7 will be bounded by 1. Now, but we want to express x near around 4, because we want to see how close to 4 does x have to be. We want to answer this question, so that now we subtract 4 to make eventually here x minus 4 and absolute value of x minus 4. So by subtracting 4, we reach this one, so that by taking absolute sign, now we can reach at this one. This inequality is same as that one. So here, the conclusion is that this one will be satisfied whenever x is chosen, satisfying this inequality, so that once x is, the difference between x and 4 is less than half, then always now the value of f from 7 is bounded by 1. Okay. Here, and so here in general, now for given f of x, right now we are using this one. Now, if we choose arbitrary epsilon, arbitrary party number, it can be very small. Then here there exists a number delta, of course, depending on epsilon positive, such that now whenever x minus 4 is bounded by delta, then fx minus 7 is bounded by epsilon. In the above example, and epsilon is 1, then we have found delta is 0.5. By using this same argument, you can see that if you choose epsilon is 0.01, then you can get delta is 0.05, 0.005. So in general, looks like if delta is half of epsilon, then and now always that inequality is satisfied. So once x is close to 4, then the value of f and at x is now close to 7, and this along with arbitrary tolerance, you can say that. So from this observation, we can define the limit more precisely in this way. Now, fx is defined on an open interval about a near around a. Possibly, f is not defined at the point a. It can be defined, but it may not be defined. It doesn't matter. So we say that the limit of fx as x approaches a is L, and we can write in this way if this is satisfied. For every choice of epsilon positive, there is a corresponding number. Of course, delta is depending on epsilon, such that as far as you are choosing x satisfying this inequality, so that in horizontal direction, this one makes delta interval. So let's say in this way, there's a, and that is now a minus delta, and then this is a plus delta, and excluding that point a, if x is chosen inside this interval, then here fx minus L is absolute value is bounded by epsilon. So that means x is close to a, then now function value at x is close to L. So that is a precise definition. Once it is satisfied, then we say the limit of fx as x approaches a is L. Okay. Here, I write down here now, note, the value of f at x equal a does not change the existence of limit. And also, in this definition, larger than 0 means that we exclude x equal a. And such a definition is called now epsilon delta definition of the limit, or simply epsilon delta argument. Now, again, we'll try to solve one more problem. We try to use definition 2.22 or thereon to show that limit x approaches 1, 5x minus 3 is 2. Okay. And start with this one. And 5x minus 3, and in fact 5x minus 2, and modulus is bounded by, now whenever x minus 1 is bounded by delta. So for arbitrary epsilon, we have to find the delta depending on epsilon. So here we start with fx minus 2 as in this earlier example. Okay. And here, so the f of x is 5x minus 3. So we can reach it that one. Okay. So this is bounded by epsilon, and 5 is common and go out and divide by 5. So we can reach that one. because we have to deal with now eventually that inequality. Already we obtain the shape. So the absolute value of x minus 1, this shape appeared and bounded by epsilon over 5. So that now we can choose that is delta. So that once x minus 1 absolute value is bounded by delta epsilon over 5, then now fx minus 2 in modulus is bounded by epsilon. For any epsilon, you can choose very small, 10 to the minus 10, 10 to the minus 1 million. It doesn't matter, even though it is arbitrarily small. Now, once delta is chosen in this way, then always this one will be satisfied. So basically, in this definition, this line 2.15 must be satisfied. Then we say that the limit of fx is L. So we prove that. Okay. Now in this proof, you can choose delta and here more flexibly. We choose delta very tightly, but delta can be smaller than that, so that you can choose smaller interval. In fact, this one is, in a sense, maximum best fitting delta, but you don't have to choose best positive delta. Just one will work, so that you can say delta is epsilon over 10. That will work also. Okay. Now let's try to solve this problem. For that, the claim, let's try to find the delta such that here, when epsilon is 1, and we find the delta so that this this line is 2. Okay. So here, to solve this problem, okay, we start with this one, so that square root of x minus 1 minus 2, that is now bounded by epsilon, but epsilon is chosen to be 1, okay, a specific value. Now to solve this one, okay, here we eliminate the absolute sign, then that is now minus 1 left lower bound, and that is the square root of x minus 1 minus 2, and that is 1. Now, we have to get x and lower bound, upper bound, so that we try to undress in a sense and eliminate the terms. So in this case now, add 2. Then that one will be here 1. Now that is square root of 1 minus, oh, no, that's x minus 1. Okay, that is now x minus 1, and that is by adding 2, it will become 3. Now we square them, and then here we have 1, and now x minus 1, that is now, oops, I try to make here now the equality sign, but it's wrong. So here x minus 1 and 9 again, and here now add 1. Okay, then here 2 and x and 10, right? So we found here the interval of x. If x is between 2 and 10, then now that will be satisfied. But we want to find this form, so that we have make this form. Okay, so try to make subtract minus 5, so that here we have minus 3 and x minus 5, and that is here we have and 5. So that is now, okay, if you try to, okay, so if you specify then, because the quantity in modulus, they are not the same. If a minus 3 and this is 5, but anyway, along with a smaller one, you can reach at that. That is now, if you are writing, for example, that is bounded by 3, the absolute value of this one, smaller one, then now this direction is not working, but that direction is working. In fact, earlier one is both sides is working, so that is the answer. So delta will be 3. Okay, pictorially, let's try to explain from here to there. Okay. Now, x is between here, that is 2 and 10. Now, we have to find the interval, and in this form, so 5 is around there. That is a 5. So that now, if we want to make this form, then this length of 3, so that again, that length of 3, so that will be 8. So we are choosing only this sub-interval such that now you can write down from here to there, like x minus 5. The distance from 5 is bounded by now 3. Then this choice is part of this original one, so that direction is okay. And so along with that choice of delta 3, that inequality will be satisfied. Okay, because we have to write down in this form. We chose part of the interval x can be. Okay. Here, summarize the strategy and the process of finding delta is given in this way. And basically, we have to solve the problem. For given epsilon, we have to find the delta. So epsilon can be given and along with a specific number, or just simply epsilon. Anyway, epsilon is given, we have to find the epsilon. In order to do that, first we have to solve the inequality. Here, fx is practically a function of x. And then, as in this example, you can find the interval for x. In this case, the c is 2 and d is 10. So interval CD can be found. Of course, here now, a is 5, so that between 2 and 10, 5 is included. Okay, and then, to make the shape, so eventually, now in subinterval is chosen, there is a 2 is, in fact, 5 now minus delta, so delta 3, and now 8 is basically 5 plus delta, right? Okay, so we chose such subinterval of CD, and we can find the delta. So by using exactly the strategy, we solve the problem. So here, finding delta is not a big problem. And of course, we chose delta 3, but you can choose less than 3. It doesn't matter. Just if you choose delta is 4, then you have a problem. But if you choose delta is 2 or 1, then also it'll work. Okay. Now, from exercise, we have here one challenge problem. We want to prove here limit x approaches a with square root of x is square root of a. Now, you have to, okay, so that in what you have to do is that, in fact, square root of x minus square root of a absolute value is bounded by epsilon whenever now x minus a is now bounded by delta. You have to find the delta for given epsilon. Epsilon is not given specifically, so that you have to work with general epsilon. So here hint is given, and for that term you can write in this way, so that if it is bounded by epsilon, then from here you can get x minus a absolute value is bounded by epsilon. Now that is square root of x plus square root of a. Okay. So in x is near around a, so x is now not really stationary, so that you have to deal with this one nicely. And also you can choose delta such that here smaller than this upper limit. Right now that one is sort of upper limit, and best fitting now delta, so that rather than best fitting delta, you can choose smaller one, any smaller one. So it's guaranteed the smaller one. It's fine. Now already you may imagine, already you may think of some solution out of my comment, and now try to finish the solution yourself. Okay, this is the end of the section. Thank you.